Good morning, good evening, good afternoon. Welcome to the first ever Yance video series about displacement from velocity versus time graphs, everybody's favorite topic. Today's broadcast is sponsored by coffee. Keeps me running every single day. Shout out coffee. So, we're going to start today with a little recap over our friends distance and displacement. So, distance, if you remember, is the total length of the path traveled. So I could wake up in the morning, I'll drive to school, and then I'll drive back home, and my total distance for that day might be 50 miles. Okay? And distance is a scalar, which means it only has magnitude. We don't care about what direction you went during that day. We just care about how far did you go. Now, our other friend, displacement, is just simply a change in position. So that could be from start to end, that could be a change in position somewhere during the motion, but it's simply a change in position. So if we use that other example, if I wake up in the morning and I drive to school and then I drive back home, my distance would be 50 miles. My displacement, though, would be 0 because I started and ended at the same place. So that means that our displacement has to be a vector because it has both magnitude and direction. Now, if you're somebody out there who does not know the difference between a scalar and a vector yet, please commit those things to memory. Scalar only has magnitude, vector has magnitude and direction. So those are very important things that you need to keep in mind. Alright, now, velocity, how we calculate that, is just simply a change in position divided by a change in time. Now, velocity is also going to be a vector because, and if you want to remember it this way, we use displacement to calculate velocity. And since displacement is a vector, that means velocity must also be a vector. Okay? Velocity is a vector, and an example of that we could use is that if I am driving to school, I might be driving at a rate of 50 miles per hour. Now that right there is simply a speed because it does not have a direction. But if I were to say 50 miles per hour north, then that becomes a velocity because I have a direction right here, north. That's my direction. Okay? Now we calculate velocity using this equation right here, a change in position divided by a change in time. Now if we expand this out, a change in position is just simply x final minus x initial. X final minus x initial divided by a change in time, and that's equal to our velocity. Okay? We talked a lot about that. This right here you can also get from a position versus time graph. So that's what we're going to talk about next. So position versus time graph. Here's our friend. We've been working a lot with these guys right here, a position versus time graph. So looking at this guy right here, position versus time graph. I've got my position on the y-axis and I've got my time on the x-axis. And right here, if I were to describe the motion of this object, let's see here, I'll use orange. Let's call this section 1 and this section 2. In section 1 of my motion, I'm moving at a constant speed in the positive direction. Okay? Moving at a constant speed in the positive direction. Now, if I wanted to find out what my displacement in that first section of motion is, I totally could. I could say displacement is equal to my change in position, so my final position minus my initial position. And looking at this, I start here and I end here for that first section of motion. So my final position right here is 10 meters. My initial position here was 0 meters. So all I say is 10 meters minus 0 meters, and I get that my change in position is equal to 10 meters for that first section of motion. Alright? Now, if I wanted to calculate the velocity for that first section of motion, I could totally do that as well. So remember, velocity is equal to our change in position divided by our change in time. So looking at this first section, my change in time would be 0 to 5. So I'll come down here. Velocity is equal to change in position divided by change in time. I'll plug my numbers in. My change in position was 10 meters. My time, 5 seconds. So I get that my velocity for section 1 should be 2 meters per second. Alright. Now we can do the same thing for section 2. So section 2, I'd say, do that over here, make a nice line. Section 2, I can say I'm moving at a constant speed in the negative direction. Now if we work through this same process, I'll get that my change in position, my final position here is 0. So right here this would be 10, 0. Up here this would be 5, 10. This right here would be 0, 0. So my final position in the second section of motion would be 0 meters. My initial position for that second section of motion would be 10 meters. So 0 minus 10 meters. And my change in position would be a negative 10 meters. Remember, that negative is very, very important because displacement is a vector, and that negative indicates the direction. Then I can calculate my velocity to say v2 is equal to a negative 10 meters divided by 5 seconds, and I get that my velocity should be negative 2 meters per second. Alright. Now we've done a lot of this, so the next step, as we've been doing, is I can take all of this information and translate it into a velocity versus time graph, which I've already done. I've got my first section of motion here at a positive 2 meters per second, and then I've got my second section of motion here at a negative 2 meters per second. So now it brings us to our question, how could we figure out what my change in position or my displacement is only from this velocity versus time graph? So let's first look at this equation, how we calculate velocity. Remember, velocity is equal to a change in position divided by a change in time. Now I can calculate change in position from that equation. All I need to do is just rearrange it. So I can rearrange it by multiplying each side by a change in time. Cancels out there. And I get that change in position is equal to velocity times a change in time. Now if I'm looking at my velocity versus time graph, well, velocity, that's on my y-axis. Change in time, that's on my x-axis. So if I come over here to section 1 on my velocity versus time graph, and if I look at my previous work, I should get a positive 10 meters for my displacement for that first section of motion. So if I look at this first section of motion, I can kind of make a square out of this. Okay? So what I mean by that is I can extend this line down here, and then suddenly I've got this area here. Now let's just think about finding displacement as calculating the area under that line. Because look at this. I've got a y-axis, which my y-axis could simply just be this side of my rectangle. So here's my velocity. My x-axis, my delta t, that's just another side of my rectangle. So I got my delta t right down here. Now if I multiply v times delta t, I'm going to get the area under that line, which is also going to be equal to my displacement. So let's plug those numbers in. Let's say that my displacement for section 1 is equal to v. So my v here is equal to 2. My delta t here is equal to 5. 2 meters per second, 5 seconds. I plug those things in here. I get 2 meters per second times 5 seconds, and I get that my change in position for section 1 is equal to 10 meters, which that conveniently matches up with what we expected up there. So there's section 1. Now the same thing should happen for section 2. Now remember though, displacement is a vector, okay? So it needs to have direction. So when we do section 2 here, we need to make sure we account for the fact that this velocity is negative. So I'm going to do the same exact thing. I'm going to turn this into a square or a rectangle. My velocity here is going to be equal to negative 2 meters per second. My delta t is going to be equal to 5 seconds. So then I just take those over here. Got my section 2 calculation. And I can say that my change in position for 2 is equal to a negative 2 meters per second times 5 seconds, which is then equal to a negative 10 meters, which conveniently matches up with what we expected. Now looking at this position versus time graph, I start and end at the same place. So my total displacement should be equal to 0 meters. Well, if I look at what we just calculated down here, I see that that checks out, because if I say my total displacement is equal to change in x1 plus change in x2, I'll see that my total displacement is equal to 10 meters plus a negative 10 meters. So my total displacement is equal to 0. And that concludes my video. Yance out.